Good evening, everyone. Welcome to the week 4 live interaction session for the course Bioelectrochemistry. As usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. Let me just share my screen. I hope my screen is visible and I am audible. So, let's start. Good evening, everyone. I welcome you all to the week 4 as well as the last live interaction session for the course Bioelectrochemistry. This course is offered by Professor Mainak from the Department of Biological Sciences and Bioengineering from IIT Kanpur under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I am one of the course team member responsible for conducting the live interaction session for this course in the Jan to May 2026 semester. So, in the last three live interaction sessions, we have gained a lot of foundational understanding on the electrochemistry and electrochemical principles governing the various types of systems. So as such, we started with the definitions, the basic definitions that are commonly used in the field of electrochemistry. Then we discussed about the different types of cells, the galvanic cells, and under galvanic cells, we discussed about its architecture, the different types of electrolytes and electrodes that can be used. We discussed about the concept of salt bridge and its importance. Then we moved on towards understanding about the Nernst equation, where we try to relate the EMF of a cell, or you can also say the potential of a cell, to the concentration of the reduced and the oxidized species in the redox reactions that is happening in the electrochemical cell. Then, in the last live interaction session, that is the week 3, we correlated or we derived the equation for calculating the EMF of the cell and its relation to that of the equilibrium constant. We discussed about the different types of about the conditions at equilibrium, how the EMF of the cell will vary. Moving forward, we also saw the concept of concentration cells, what are concentration cells and how they are typically different from a normal galvanic cell. Then we also saw how concentration cells basically gain interest in the biological field. So as an example, we discussed about the nerve conduction, where we stated that the nerve cells are also, or you can say they behave very similar to that of the concentration cells, and we discussed about its mechanism. So in this live interaction session, we are going to discuss about the different types of electrodes that are used in the electrochemical cells, and also about the redox initiators and redox proteins that is used for detecting various kinds of biological species. So, talking about the types of electrodes, so if you happen to remember, in a full cell, you usually have three different types of electrode. The first one is, or you can say in the half cell itself, you have totally three different types of electrode. The first one is your working electrode, the second is the counter electrode, and then the third one is your reference electrode. So, working electrode is the basically the way electrode where the redox reactions or any kind, or where the chemical reactions usually takes place, and we are typically interested in deriving the potential from the working electrode. Counter electrode is often used as a electrode which basically helps to complete the circuit. The third type of electrode is the reference electrode. So the reference electrode is typically used to measure the standard, it's typically used to measure the potential of the working electrode. So there are different types of reference electrode often used. So let me just write it down. So if you speak about reference electrodes, there are there are different types of reference electrode, but as far as the course is concerned, we will discuss about the three basic type of reference electrode that are commonly used in the electrochemical experiments and electrochemical cells. So the first one is your SHE, that is nothing but it is the standard hydrogen electrode. Standard hydrogen electrode, or also it can be called as NHE, which is nothing but normal hydrogen electrode. Then I hope all of you are able to recollect our discussion related to the standard hydrogen electrode, its mechanics on how it is used as a reference electrode, its structure and construction. So the second one is the AgCl electrode, and then the third one is the calomel electrode. So often AgCl and the calomel electrodes are the reference electrode which are commonly used. Standard hydrogen electrode always remains as, in most of the cases, remains as a thermodynamic reference. So my question over here, what I want to put forth is, why is when SHE or NHE, the E naught value is going to be 0 volt, then why it is not, why it only remains as a thermodynamic reference, and why it is not used in the electrochemical cells, in practical electrochemical cells? Anyone with any idea on why is SHE always remains as a theoretical reference, but whereas in case of the practical electrochemical cells, we use AgCl electrode or calomel electrode as reference? Anyone? It's quite simple. Think from better to think from the perspective of the states of matter that is involved in while doing the SHE electrode, the construction of the SHE electrode, standard hydrogen electrode. Yes, anyone with any answers? Okay. So typically the reason being is that in case of the standard hydrogen electrode or also the normal hydrogen electrode, the electrode typically uses hydrogen gas as its source. So as all of you know, H2 gas is very flammable. So maintaining a continuous flow of hydrogen gas is difficult, and also it is going to be risky because it has the potential to catch fire. Has a it is fire hazard. There is a fear for a fire hazard. So due to that, the standard hydrogen electrode usually remains as a thermodynamic reference. So the first thing is, it is very difficult to maintain. Difficult to maintain because you use gas. So a constant pressure is difficult to obtain. And the second reason is hydrogen gas is flammable, thereby creating a fire hazard. However, if you see in case of AgAgCl or that of the calomel electrode, both these limitations are eliminated. The major reason being is that the AgAgCl and the calomel electrodes are usually are in solid state. They are in solid state. So that is the main advantage which is both these electrode carry with them. And the second thing is they are sealed and they are safe. And apart from that, they have the ability to provide a constant potential, and that potential fluctuation in case of AgAgCl and the calomel electrode is not going to be very high. So they are in solid state, they are sealed, and it is safe to use, unlike the fire hazard in case of the standard hydrogen electrode. The second thing is that it helps to provide a constant potential. The potential often fluctuates in the order of microvolts. So, due to which AgAgCl and the calomel reference electrode are often preferred in electrochemical cells. So anyone who knows what is exactly this calomel electrode is, I mean its chemical composition, like AgAgCl is one of the reference electrode. The other standard reference electrode is the calomel, but calomel has certain chemical composition. Anyone, any idea on this calomel electrode? Yes, calomel electrode. So its chemical composition is Hg Hg2 Cl2. It is primarily based on mercury. So this is the chemical composition of calomel electrode, just in case if some of you don't have any idea on this. So calomel electrode, the chemical composition is, it is based on Hg, Hg2, Cl2. So typically the reaction for the calomel electrode is something like this. Plus electron. Is it fine? So this has a E naught value of 0.268 volt, and your AgCl has a E naught value of 0.1997 with respect to, again, both of them are with respect to SHE. So kindly note that down, and please have a look at the respective reactions for each of these electrodes, which will be quite useful. So typically the construction of AgCl and the calomel electrode, if you see, you basically have a Ag wire which is encapsulated with the AgCl, and this system is usually filled with the saturated KCl solution. So in both these cases you have saturated KCl. Now this arises a question to us, why is this saturated KCl used in these reference electrodes? Oh, just a second. So let me just share my screen once again. Yeah. So the question was, yeah. So the question was, why is saturated KCl used in these reference electrode? What is the role of KCl, saturated KCl? Anyone? Any idea on what is the role of saturated KCl? Because if you see in both these electrodes, we write the reaction with respect to Hg or Hg2Cl2, but it also consists of saturated KCl in them. So this KCl remains, or usually these reference electrodes are kept under saturation condition, and for that we use KCl. So question is, why KCl is used, saturated KCl? Why these reference electrode need to be filled with the saturated KCl? So the answer is, what usually happens is, the Cl minus ions that are there within this liquids or in both these calomel electrodes, there are chances that over a long period of time, as well as along with the continuous operation of these reference electrodes, there are chances that these liquids may evaporate. So due to that, what happens is the concentration of the Cl minus ion, or to put specifically in electrochemistry term, you can say that the activity of the Cl minus ion usually gets altered. So in order to minimize that, we typically use KCl as a we use KCl solution to make sure that the concentration of the Cl minus ion remains stable, or the concentration of the Cl minus ion is maintained in these reference electrode. And moreover, KCl usually has, since it's a saturated KCl, the amount of ions will be more, so that usually helps in lowering the internal resistance and increasing the conductivity of the system. And third thing is, K plus and Cl minus ions typically have ionic mobilities in the or in a similar order, so due to which there will be the any kind of potential mismatches will be not there if you use saturated KCl. So that is predominantly the three reasons why KCl is often used. So again, this is about the reference electrodes, their operation, and then the way they need to be maintained is requires expertise. So there are a lot of content on how to maintain these reference electrodes and how to service these reference electrode in case of any problem if it arises. So I encourage all of you to watch some of those videos. After the end of this session, I will post link to few of these YouTube videos which I personally used while dealing with these reference electrode systems. So they will be quite useful for you to understand that reference electrode does require some amount of maintenance, and there is a correct way to maintain these reference electrode. So this is overall about the reference electrode as such. Next, we move on towards the concept of indicator electrodes. So indicator electrodes are those which typically responds to the analytic activity. Analytes are those which are nothing but the electroactive species in the system. Next, we come to the concept of indicator electrodes. So indicator electrodes are the ones, those which respond to, just a second, analyte activity. If anyone has any questions on what is an analyte, it is nothing but it is the electroactive species that is present in the system. So these indicator electrodes are usually of two different types. The first one is the metal electrodes, and then the second one is the ion selective electrodes. So in case of the metal electrode, so the basic mechanism in which both of these electrode actually responds to the analytic, or which respond to the analyte activity, is different. So in case of the metal electrode, usually the response is in the form of a redox activity, the redox reaction that happens on its surface. The metal surface. Whereas in case of the ion selective electrodes, it is dependent on the selective ion binding to the membrane. So here what typically happens is few ions, selective ions, bind to that membrane. So due to this selective ion binding to the membrane, a potential is usually generated, a voltage difference is usually created across the membrane, which is why you get that potential difference is what is usually harnessed. So it's something like what we discussed related to the nerve cells. So there we discussed about how the concentration changes usually leads to the generation of the potential across the membrane. So similarly here also in case of ion selective electrode, the selective ion binding usually results in the binding to the membrane usually generates the potential. So these ion selective electrodes are the ones that have greater interest in the biological application, because majority of the biological systems often use or often behave like ion selective electrodes, and they generate potential. Metal electrodes are typically in case of the are not very common, you can say, in the biological application. However, ion selective electrodes are very popular in biological applications. Greater interest in biological applications. So this is a very short overview on the metal electrodes. So if you talk about different types of ion selective electrodes, you have something called glass electrode, you have solid state electrode, you have liquid based electrode, and you also have something so called as an compound electrodes. So before discussing on that, let's discuss about the metal electrodes for some more time. We try to gain a little bit more understanding on this metal electrodes before we actually move on towards the ion selective electrodes. So anyone with any questions so far? So we are talking, or I mean discussing about the indicator electrodes. So the first one is basically the metal electrodes. Second one is the ion selective electrodes, where selective ion binding happens to the membrane, and that typically presents or is of a greater interest when you see from the biological perspective. So typically in case of these metal electrodes, we are interested in knowing the concentration of Ag plus ions. We try to measure the concentration of the silver plus ions, and for that we typically use two types of electrodes. One is your platinum, and then the second one is your gold. Why these two are used as electrode? We know the reason already. I hope everyone is able to recollect why platinum or gold is used as electrodes. Yes. So typically the reason is being that platinum and gold are inert in nature, so they are not going to react with any kind of electrolyte species. I mean, as such they are not going to react. There is no chemical reaction that is going to happen between the analyte and the platinum surface. So this platinum on the gold surface, they basically transmit the electron from the electrode to the solution, or basically they try to pull the electron from the solution and they transmit them. Now the question arises is why specifically gold and platinum? Because this particular part of pulling this electron from the solution and then transmitting them basically requires high electrical conductivity. So if you see gold has good electrical conductivity. So the reactions that usually happens on the surface is going to be very fast. So that is typically the reason why platinum and gold electrodes are used. However, here comes that actually comes with a trade-off because of its expensive, because of its high cost. So in order to combat this problem, carbon based electrodes are often being used. The major reason why carbon based electrodes are used for these kind of are used in place of these metal electrodes is basically because of the fact that carbon materials are usually cheaper compared to the platinum or the gold metal electrodes. And the second thing is that the transfer kinetics, the electron transfer kinetics for these carbon based materials are usually very high. The transfer of the electrons from the electrode surface or in the electrode surface for carbon based materials are usually very rapid. So that typically enhances the sensitivity of the systems. So that is the reason carbon based materials are also widely explored for these as a replacement for these metal electrodes. So if when I say about the carbon based electrode, I specifically what do you say, talk about the reduce the graphene oxide or graphene oxide based systems. So they have a high surface area, and then and then they basically promote the rapid electron transfer on its surface. So this is about the metal electrode. In case of the ion selective electrodes, now that we are going to discuss about, we have quite a few of them in terms of the applications. So if you see ion selective electrodes, so we typically detect pH using these selective electrodes, and then we also try to detect potassium ions, and then anything else that we usually use ion selective electrodes for. Again, ion selective electrodes are very common in biological applications. Here we will try to discuss about the pH sensors and the potassium ion sensors, or you can say the detectors for potassium ions. So in case of the pH sensor, what do we usually do? So pH sensor, as such, we try to measure the pH of a system. But as such, when I mean pH, I mean the concentration of the H plus ions within the system. As you know, pH is power hydrogen. So you try to calculate the power of the hydronium ions or the H plus ions, or you can also say that as the concentration of the H plus ions. So for this pH sensor, we typically use glass electrode. So how is this electrode typically used for detecting the pH? Anyone with any questions so far? Because before we discuss, let's give a pause for some time. If you have any questions or queries, because this is more often of the application of the ion selective electrodes. So before this, we have discussed about the metal electrodes concept. So if you have any questions related to this metal electrodes, Please feel free to ask me. So in case of the pH sensor, we typically use glass electrodes. So what is the primary concept behind using this glass electrodes for measuring the pH of a system? So this is typically the place where we will use two reference electrodes, which is usually separated by a glass membrane. So by measuring the shift in the concentration of the H plus ions, we usually try to detect the pH value. So glass electrode, as in the sense, I mean glass membranes will be used for measuring the pH of a system. So here we will use two reference electrodes. One will be the inner reference, and then the other one is called as the outer reference. So in case of the inner, so I'll just first write the line diagram, then it would be much easier for people, for everyone to understand. So the so in this line diagram, this part on the left hand side refers to the outer reference electrode, and then the part on the right hand side is the inner reference electrode, and both these reference electrodes are separated by the glass membrane. So usually in case of these outer reference electrode, the concentration, or you can say that the activity of the H plus ions is usually fixed. So in case of this outside reference electrode, the H plus ion concentration is already known to you. Whereas if you see in case of the inner reference electrode, this H plus ion concentration is unknown for us, and that is something that we actually want to measure. So any shift that typically happens, so these H plus ions try to bind to these glass membrane. Bind to the glass membranes. So any shift that is happening within the system will basically cause a change in the delta V that is observed, because when the H plus ion binds to that of the glass membrane, there is a potential difference which gets generated. A potential difference is generated, voltage is getting generated. So any shift, and we know, and we can quantify that. So any particular, and that we can quantify that, and then that is typically maintained as a standard. So any shift that is happening within the system basically causes a change in the delta V. So by measuring the changes in the delta V using a voltmeter as we do, we can actually measure the change in the concentration of the H plus ions, which can, which through which we will be able to determine the pH of the electrode. So it's like this: H plus ions is binding to the glass membrane, so because of which a potential difference is generated. So for a standard solution, we know what potential difference is usually can be obtained by, if there is any shift within the concentration of the H plus ions, a potential difference or a voltage difference is generated. By measuring the potential difference or the voltage difference, you can measure the concentration of the H plus ions. By measuring the concentration of the H plus ions, you will be able to calculate the pH. So this is the concept of a pH sensor. Similarly, in case of the potassium ions, for detecting the potassium ions, same principle is used. However, there, instead of using glass as a membrane, you use velomycin. This velomycin membrane binds with the potassium ions and transported inside the membranes. So because of this binding, a potential difference is generated, and that is what is typically getting measured. So any kind of a change, so once you know a particular standard, and once a standard is fixed, any shift from that particular standard can be used to calculate the concentration of the particular ion. Only thing that we need to maintain here or know here is that particular membrane that we are going to use for the system should have higher binding affinity with that particular cation or the protons that is under consideration for the study. So for potassium ions, valinomycin. So the potassium ions bind to these membranes. That binding typically generates a potential across the membrane, and that is what is measured through the voltmeter. By measuring that, any shift in this activity typically results a change in the typically results in the change in the delta V value that we obtain through the voltmeter, and by comparing that with the standard that we have, we will be able to measure the, or you can say detect the concentration of the K plus ions. Only the thing that we need to maintain in case of these ion selective electrodes is that the membranes that are typically used for binding these selective ions, their affinity to those selective ions needs to be high, or otherwise the readings, and you can say the measurements, will be inaccurate. So try to keep these things in mind. So the concept is the same. It's about binding of the ions to the membranes. It's just that what membrane is used where and how that binding is happening differentiates different types of electrodes for measuring different ions in the system. And majority of the biological applications, or measuring the concentration of the ions in biological system, usually use these ion sensitive electrodes. So in both these cases of metal electrodes as well as ion sensitive electrodes, or whatever we have discussed so far, we usually measure the potential difference between the electrodes, that is between the working electrode and the reference electrode. So this kind of measurements of the system is called as potentiometry. So here we basically measure the cell potential by keeping the current value as 0. So that is what is called as potentiometry. Now after this, for calculating, or you can say for detecting, or you can say for measuring other kind of species within the biological application, there are certain other techniques, but those techniques do not usually work on the principle of constant current, or you can say of measuring potential difference, whereas they usually work on the principle of measuring the current as a function of time by keeping constant potential. So those kind of techniques are called amperometric techniques. So the thing that you need to, or that we need to understand here is, potentiometric, you basically measure the potential difference between the electrodes. In case of amperometric, you measure the current by keeping the cell potential as constant. So in case if you have anything to ask, then let me know, or we can actually move forward to discussing about two other concepts on calculating the concentration of dissolved oxygen and the glucose sensor. Anyone with any queries? Yes, anyone, any queries? Please explain velinomycin. Aditya, what exactly do you mean? I mean, about explanation for this velinomycin? Is it the principle of how they bind, or because here you typically need to understand that, I mean, the major thing that we are trying to focus here is, they try to bind, and using that binding as a principle, we try to measure the concentration of the K plus ion. If you are specifically interested in knowing how this valinomycin interacts with K plus, then I would suggest you to go through some of the sources in the internet of how this valinomycin interacts with this K plus ion, and how, if you are specifically interested in what kind of chemical interaction happen, then it is because our main principle here is to basically show that how melanomycin membranes are used for measuring K plus ions. So that particular, we want to keep the concept simple. So if you are interested, then you can discuss, you can go about it, or also probably I might include a slide on that later while uploading the lecture. So, moving on towards this dissolved oxygen, the last part, I'll just write the reactions and how, and just explain how this measurement is usually done. So, as I said, these are typically amperometric techniques where we actually try to measure the flow of current. So, basically, by seeing the difference in the current, we usually measure the concentration. So, if you remember, in case of these other techniques, that is this for K plus ions as well as the H plus ions, we measure the change in the potential. But in case of this dissolved oxygen and glucose monitoring device, we are going to measure the current. And by seeing how the current decreases or increases, we will be able to correlate that to the concentration of the oxygen in the system. So here we use cathode. There are two reactions as such, cathode and anode. So typically here also platinum or gold is used as a cathode and cathode. Just a second. So in case of the cathode, if you see, the reaction is oxygen interacts with 4 H plus ions, or binds with them, you can say, plus 4 electrons gives 2H2O. And in case of the anode, you have 4Ag that reacts with the 4Cl minus. Mm. So this is typically the reaction. So here we try to measure the flow of the current. So that 4 electrons that so whatever that gets generated at the anode, it usually goes to the cathode and then gets consumed there. So in that particular process, we basically try to measure the current flow, and based on the current, we try to obtain the concentration of oxygen. So this is the principle of how do you see the dissolved oxygen. So we have a standard, and based on that particular standard, we know that if this much amount of current comes, then this will be the particular oxygen concentration. Now based on the shift in the oxygen concentration, the current will be affected. Based on that change in the current, we can correlate to the change in the concentration of the oxygen in the system. Next is the glucose monitoring system. A very common glucose monitor, which usually used to measure the glucose content in the human blood. So this concept, so the basic fundamental remains very old, and significant improvement in these glucose monitoring devices are being carried over. So over the years, starting from going for high end or high for going for invasive techniques, we have come to a stage where again those techniques are still not very mature, we have come to a stage where we can actually measure the concentration of the glucose using human sweat and human breath. So those concepts still are not very matured enough. So there are still trials going on with understanding how accurate these calculations and measurements are. But the basic fundamentals behind this glucose monitoring systems is actually the same. So in this case also, if you see, AgAgCl is used as a reference electrode, and the typical principle is that the glucose reacts with the oxygen in the presence of mm, so here we use an enzyme, which is the, just a second, 1 minute, let me show it up in a proper way. In the presence of glucose oxidase is the enzyme. So to give gluco glucone lactone, just a second. Yes, plus H2O2. So if you so this particular reaction happens only in the presence of glucose oxidase. In case of the absence of glucose oxidase, glucose reduction is not possible. Here the concentration of the glucose is usually measured by the concentration of the H2O2 that gets generated within the system. So the device usually monitors the concentration of the usually monitors the electric current, which that flow of the electric current is proportional to the concentration of the H2O2, which is directly proportional to the concentration of the glucose in the blood. Now the question is, how is this current flow and the concentration of the H2O2 is related? So for that the reaction is, so based on this, based on the flow of the current, we will be able to measure the concentration of the hydrogen peroxide in the system. By measuring the concentration of the hydrogen peroxide, we will be able to measure the concentration of the glucose. Again, one of the major problems of the glucose monitor is that their response typically depends on the oxygen concentration. When I mean oxygen concentration, what I mean is how much this oxygen gets linked or comes in close contact with the glucose oxidase. So if that contact is not that high enough or good enough, then the measurement will be inaccurate. In order to basically combat this problem, people use, or I mean the concept that is used is that to add a mediator. That mediator is 1 comma 1 prime dimethyl ferrocenium ion, a ferrocenium cation. So by using this as a mediator, we basically improve the efficiency of this oxygen interacting with the glucose oxidase and the glucose thereby resulting in hydrogen peroxide, accurate amount of hydrogen peroxide production, which helps in measuring the concentration of the glucose. So this is about the glucose monitor. So the part where we are discussing on the concepts ends here. So there is another one concept on redox proteins. So there the principle is usually how the proteins bind to the surface, and based on that they usually measure the electric potential, and based on that cyclic voltametric curve you will be able to obtain the concentration of the protein. So typically speaking here, all these kind of electrochemistry techniques usually rely on the flow of current or the voltage. Their change, that particular change in the current or the voltage, that difference is used for measuring the concentration of that particular material of interest. So with that we come to an end of this particular discussion on the concepts. We have few questions to discuss before we can wind up. So we are almost left with around an hour or so. I mean, I guess at least 50 minutes are there with us. So let's move on to this. If you have anything to discuss, then please let me know, or else please go forward with the questions. So the first question is, which of these is not used as a reference electrode? Very simple one. AgAgCl, calomel, standard hydrogen electrode, CdCdCl2, cadmium or cadmium dichloride. So which of these following is not used as a reference electrode? That should be quite a simple one, right? Anyone? Oh, CD, yes. So the other three can be used as a reference electrode. However, as I said, standard hydrogen electrode is often referred to as a thermodynamic reference. It is not very commonly used as a reference electrode, but again, it is one of the reference electrode that was first used. After that, we did come up with this thing owing to the problems that hydrogen is very flammable and very difficult to maintain the system. But still, standard hydrogen electrode is one of the reference electrode materials. So the answer for this is cadmium slash cadmium chloride. Now let's come to question 2. Osmolarity can be measured by using which of the following properties slash principles? Is it the temperature of the solute, or is it the freezing point depression, or is it the color of the solution, or it is the moles of solution versus moles of water? Option D. Okay. Moles of solution versus moles of water. Is that right? First of all, what is the meaning of osmolarity? Meaning, I mean, definition for osmolarity. So, osmolarity is nothing but it is basically the number of solute particles that actually contribute to the osmotic pressure in the solution. Am I right with the definition? Osmolarity means number of solute particle that contributes to this osmotic pressure in a particular, I mean, for 1 liter of solution. Yes, that is also almost correct. So question over here is, how do you actually going to measure the osmolarity? So it is the number of moles of solute, right? So however, the option D says moles of solution versus moles of water. So it's moles of solution versus moles of water. Is that right? Based on what you have defined or what definition I have given, is it fine to say it is moles of solution versus moles of water? How do you define molarity as such? Let us leave about the discussion on osmolarity. As such, molarity, when we discuss, how do we define that? Number of moles per liter of solution. Yes, exactly. So when you are going to have number of moles of what? Number of moles of solute per liter of solution. So in case of osmolarity, it is going to be, that is the reason, to put it in a simpler terms, I mentioned number of moles of solute particles that contribute to osmotic pressure divided by the volume of the solution. But here it, the last option says moles of solution versus moles of water. So with that, can we be able to determine the osmolarity? because we are not going to know the moles of solute. So it is clear that color is not going to be an answer, and the temperature also is not going to be an answer, because by measuring the temperature of the solute you do not actually have any understanding on the osmolarity. So those two are cut from the option, because color of the solution is just a qualitative measurement and not a quantitative one. So this is out of the equation, these two. Let me just highlight. Now there are two options. One is freezing point depression and another one is the moles of solution versus moles of water. So any idea on what is freezing point depression? The concept of freezing point depression, colligative properties of a solution. So if you know this concept, it is where by adding solute to a particular solution, you can either elevate its boiling point or you can depreciate its freezing point. Any previous, I mean, this we would have studied it earlier in chemistry sometime back in school days, but are you able to get the point of freezing point depression? Cryoscopic constant. Mhm. I am not aware of that term, but usually for finding out the concentration of the solute, one of these ways, because since you are not knowing how many solute particles are usually going to be present in the system that is going to contribute to this particular property, by knowing the changes in the freezing point, you will be able to correlate that to the concentration of the solute particles within the system. So the answer is freezing point depression and not moles of solution versus moles of water, because by knowing moles of solution versus moles of water, you are not able to directly get the moles of solute particles within the system, and especially that should contribute to this osmotic pressure. So freezing point depression, and moreover, um, in order to, how do you actually measure the solute particles within the system, moles of the solute particles? So that is again another one difficulty, right? So by knowing the freezing point depression, you can easily say that this much amount of the solute is within the system. So I hope there is a bit more clarity related to this on this freezing point depression. So moving to question 3, the voltage of an ideal pH electrode changes by dash millivolts for every pH unit change of analyte activity at 25 degrees centigrade. So how many millivolt change will be there in the voltage for every single unit of pH change within the system? Like if you change pH by 1, how much difference will be there in the voltage? And this should be 51.96. Oh no, sorry. This is 59.16. Yes. The options are right. So how to calculate question 3? You need to use equations and then calculate. You need to correlate EMF of a cell to that of the pH. Oh. Try to write the equation first, then substitute that in the EMF Nernst equation. Then you'll be able to determine the voltage. I mean, voltage change. If you want the equation, then let me just. So let me just paste that equation here. But you need to again rewrite. So, like rewrite in the sense, substitute their respective values. So I'll just write the expression, let me take this to a new slide. So usually, how do we calculate the pH? We usually do it through this standard hydrogen electrode, right? So the reaction is, so with respect to this particular equation, we are supposed to substitute this in the Nernst equation and then calculate the change in the EMF of a cell. So since the number of electrons that are involved in the process is 2, I'm writing n value as 2 times log. So depending upon this equation, it is going to be h plus, sorry, h plus square divided by the partial pressure or the pressure of H2 gas. Is this fine? Oh, just let me write it this way itself so that it is better clear. Is this fine? And you can take this pH2, that is the partial pressure of H2, as 1 atmosphere. So if you do that, then E cell will be equal to E cell naught minus 0.05916, and since P the pressure of H2 gas is 1 atmosphere, so it will be log of H plus ions the whole square by 1, so that will be log of H plus ions the whole square. So log of A square can be written, log 10 A square can be written as 2 log 10 A. I hope everyone is familiar with the logarithmic identities. So if you write that, then that 2 along with the 2 in the denominator will cancel, and you will end up with log of H plus. So E cell equals E cell naught minus 0.05916 times log of H plus ion the whole square. Is this fine? Oh, sorry. Whole square I have already written it. I have already cancelled, right? So this thing, it will be this much. So can you write pH as minus log 10 of H plus ions? pH is defined as minus log. Is this fine? Minus log 10 of H plus ion concentration is pH. So if you substitute this in this previous equation, what you will come up with? E cell equals to E cell naught plus 0.05916 times pH. So let this be one equation, and then the second equation, let's assume that pH is changed by 1 unit, or you can write it like pH prime. You can write it this way. This is nothing but pH plus 1. Sorry. So now based on this, if you write the same Nernst equation, then you will get E cell equal to E cell naught plus 0.05916. As per this, it would be pH prime. So now we know pH prime is nothing but pH plus 1. So that can be written as E cell naught, or let this be E cell prime. So this can be written as E cell naught plus 0.05916 plus 0.05916 pH. Now we know E cell naught plus 0.05916 pH is E cell. So then you can write E cell prime equals to E cell plus 0.05916. Now what we are asked is the difference, right? So we are asked about how much will the pH change if we increase, how much will the EMF of the cell change if the pH is increased by 1, by a single unit. So that is, it will increase by a value of 0.05916 volt. And since here the expression what we want is in terms of millivolt, so 0.05916 times 1000 is nothing but 59.16 volt, a millivolt. Is that fine? Or any confusions, any questions? How to calculate the value, or how this is calculated here? So here I am writing it only with respect to the H2 gas. Of course, this is not a complete reaction. So, but since what we want for this particular question is this much, I am not considering the other part of the reaction as such. Just a second. Okay. Any questions? So you can remember this particular expression also in case if you want, but I would prefer you to derive, everyone to derive. But in case if this is easier, then please remember, try to remember that E cell equals E cell naught or E naught of the cell plus 0.05916 times pH of that particular system. So if you do not have any question, then let's move on towards the next set of questions. While cleaning a pH electrode, it is recommended to wash the electrode with a distilled water and gently blot it with a dry tissue. Do not wipe it because this action might produce scratch on the glass, static charges on the glass, breakage, and roughness of the surface. So you should just gently blot it with the tissue. Like just place it over and then remove the water molecules that are on the surface and not wipe. Why? Is it because it will create scratch, or will it create roughness in the surface, or it will break the electrode, or will it create static charges? Static charges on the glass surface, because if you rub it, then what happens is that the charge will get accumulated on the surface, and that might create some problem while measuring the pH of the system, because just by wiping you will not create any scratch on the glass, or roughness of the surface will not happen. Breakage is not possible only with wiping, given as a condition. So it is static charges will be created on the glass, and that electrostatic charges that are created will cause a change, will cause changes in the potential, and that will basically affect the measurements in the system. So next question is another simple one. Which of the following is not a property of valinomycin? It's naturally occurring, most selective to sodium, it's an antibiotic, it's an ion selective membrane. Which of the following is not a property of valinomycin? It's A. No, valinomycin is a naturally occurring antibiotic. It's not a synthetic one. It's naturally occurring. So the answer is that it is not a property. Is that it's most selective to sodium. So that is wrong. Valinomycin, as we discussed, it is most selective to potassium ions, K plus ions. So apart from that, yes, it's an antibiotic. It is naturally occurring. It is an ion selective membrane, but the selectivity is more towards K plus ions. Again, next question is same, but I'm just keeping the slides if you have anything to ask. Okay, so let's move. Question A. When a cell contains a boundary between two electrolytic solution of different compositions or concentration, a dash is developed due to the diffusion of various components at characteristic rates in their boundary zone. What is that thing? What is it? What potential it is which gets developed? Is it solid potential or is it pseudo potential, Nernst potential, or is it liquid junction? Oh, it is the liquid junction potential, yes. So when two electrolytes of dissimilar concentrations or that of the composition basically comes in contact with each other, a potential so called as a liquid junction potential usually arises. And this liquid junction potential is the one that basically makes that result a little bit inaccurate, because even if you see in case of the oh, just a second. Because even if you see in case of the half cells where you actually have the salt bridge, there is actually a kind of a different composition or concentration electrolytes usually meet each other. So even over there you will have liquid junction potentials. So these liquid junction potentials usually make the results a little bit inaccurate in these systems. Next, solid state ion selective electrodes uses a solid dash ionically conducting substances either alone or suspended in organic polymer material as the membrane. Question 9. D. It's in melted form. Why what about this uh, supersaturated or soluble or insoluble? Why melted form as answer? Any kind of like reasoning why? No solvent. If there is no solvent, then will it be easy for the ions to uh, conduct, or will it be difficult? So it should be sparingly soluble, because the membrane as such, if you are going to be soluble, then it will not serve the purpose of deduction, right? It will totally get dissolved in the material and it will be like gone. So it should be in the form of sparingly soluble, so that the sensitivity as well as the selectivity is high, and dissolution rate is also slow. So that is the reason the solid state should use a solid sparingly soluble ion conducting substances. And in case of the melted form, what happens is conductivity actually quite decreases. So that is also one of the reasons. So shall I move to the next one or any queries? Okay, how we do not use a solvent. If you read the question here, in case of a solid state ion selective electrode, we use a solid, but that solid should be sparingly soluble. So here you should understand, it's not that we are using a solvent in the system. The membrane, the total question is that ion selective electrode is a membrane. So that membrane, whatever you are going to use, should be sparingly soluble in the electrolyte. If you are going to use a completely soluble one, then it will totally dissolve within the electrolyte. That solid substances should be sparingly soluble. For example, if you say, if you take a few of the salts, they are sparingly soluble in water. Like if you take NaCl, they are completely soluble at room temperature. But at the same time, if you take other kind of salts like calcium chloride or calcium carbonate, they are not very soluble in nature. They are sparingly soluble. Yet calcium carbonate as such, if you see, it's a solid. So like it's not about sparingly soluble solvent, it's a sparingly soluble solid. So that's the reason you have to read this word together. So solid state ion electrolyte should use a solid which is ionically conductive, sparingly soluble in a polymer organic material as a membrane, so that it does conductivity, at the same time it does not get dissolved. Oh, so sorry, there was a network issue. So let me just share my screen. So I hope this is clear. If so, then let's go on to a question. Yeah. So let's first solve question 12, then we will come to 11. So question 12 is same type of a question. Calculate the pH at 25 degrees Celsius for the following cell. So the line diagram is given. Based on this, you need to calculate the pH. You can actually have a guess over this question just by looking at the value. So let me just use this equation that was here. Mm, okay. Oh, okay, then it's okay. I'll just. So you can write E cell equals E naught cell minus 0.05916, since the pH, that cell, electrochemical cell, is operating at 25 degrees Celsius. I am writing uh, the value of RT by NF as 0.05916. But if the cell is going to be operated at a different condition, then the T will change, so this value will also change. And here two electrons are basically involved in the system, times log H plus square times nickel solid by nickel 2 plus times pH2. That is the pressure of the hydrogen gas that is being purged. So for a standard, the value is going to be 1. So here the concentration of Ni2 plus is 1 molar. The P atmosphere, that is the partial, the pressure of the hydrogen gas, here it is 1 atmosphere. So, and nickel solid concentration, that activity coefficient is usually assumed to be 1. So E cell equals to E naught cell minus 0.05916 by 2 log H plus square. And as I told, log 10a square can be written as 2 log 10a. So E cell equals E cell naught minus 0.05916 times log H plus. Now minus log 10 H plus is pH. So E cell equals to E naught cell plus 0.05916 pH. Now E cell minus E naught cell is 0.0591. So 0.0591 equals to 0.05916 pH. So if you divide, your pH will be approximately, it should be equal to 1. Which means, so if I ask what will be the concentration of H plus ions, then the value is going to be zero point 0.1 molar, because oh, extremely sorry, because pH is minus log 10 H plus, so it will be 1 equals to minus log 10 H plus. Log 10 H plus is equal to minus 1. So H plus will be 10 to the power minus 1, that is zero point 0.1 molar. This is the concentration of the H plus ion. If it is asked in the form of pH, then pH is 1. So any doubts, because we have solved two questions in the same way. Any questions? We have one more. This is quite simple one. You just need to calculate the equilibrium constant. This you can, I think we have solved one way to calculate K equivalent equilibrium. So if you want to do, we can do this now. So any doubts related to this calculation of, relating EMF of the cell to pH? And what about this question? Any idea on how to do? Yes. Any idea on how to solve this question? It's simple. You just need to know which one is cathode and which one is anode. Once you get to know that, E cathode minus E anode will be E of the cell, and sorry, E naught of the cell. Since at equilibrium E equal to 0, you need to take it this to the other side and then just do the math. So anyway, let me just solve this. So we know that at equilibrium delta G is going to be equal to 0. So delta G is minus NF times delta E. So delta E will also be 0. Sorry, minus NFE. So E will also be equal to 0. So it will be something like this: 0 equals to, for the cell I am writing entirely, E naught of cell minus 0.05916, since it's at 25 degrees Celsius, so no need to worry. Here two electrons are getting transferred, or two electrons are participating in this redox reactions. This times log of the so this would be Fe2 plus, just let me write this, Fe2 plus times copper by Cu2 plus times Fe. So if you rearrange this, it will be E naught of cell equals to 0.05916 by 2 log. This thing can be represented as as Keq, which is nothing but it is the equilibrium constant. So now we need to calculate only what is E naught of the cell. So E naught of the cell equals to E naught of cathode minus E naught of anode. So E cathode, which one is a cathode here? It is your copper, and anode is your iron. So E cell naught is E cathode, which is nothing but minus 0.4, minus of E anode is 0.5. So this will be minus 0.9 volt. Am I right? So now if you substitute, then you will be left out with minus 1.8 by 0.05916 equals to log K equivalent. If you solve this expression, you will be able to find out the K equivalent. Is this fine, or is there anything that I have made a mistake? No. Yes. Have I made any mistake or is it correct? 2. No, 2 is correct. Because two ions are participating. Two electrons are participating. Fe gives Fe2 plus 2 electrons, and copper 2 plus accepts those 2 electrons to form copper. And zero point 0.9 times 2 is 1.8. So try to identify the mistake here. There is a one small mistake which I have made. So the answer, along with the explanation, I'll post it while uploading the presentation. But please keep thinking about this. Sorry, on what could be the error. So we have almost discussed whatever we had planned for. So apart from these questions, I will also try to upload a separate one or two slides on few more problems which will be useful when you discuss about electrochemistry. So try to practice them, and since this is our last live interaction session and I'm not sure whether we will have any extra live interaction sessions, so in case if you have any doubts, please email it to me. I will respond to your queries as soon as possible. So if you have anything to discuss, then please feel free to ask. Let me just stop sharing the screen. So if there is anything, then please let me know, or I think we can conclude the session if you don't have any queries. That typically determines is dependent on. So if you see in that particular reaction, I think I need to share my screen once. So if you see in this case, Fe gives FeSO4. So which means Fe is getting converted to Fe2 plus, right? So that means it is donating 2 of its electron to form Fe2 plus. Similarly, copper sulfate here, which is in Cu2 plus, accepts 2 electrons to form copper in its elemental state, that is zero oxidation state, I mean. So the one that undergoes oxidation is the anode, and the one that undergoes reduction is the cathode, and this is general term. And in case if you do not have any reaction and to these things are given, then you need to use the electrochemical series. So we discussed this in the week 2. If you happen to see any of the lectures before, we did discuss. I did show a chart. I'm I'm not sure whether I can. Okay, we did show a electrochemical series. So of based on the potential values, you can actually say which one can be used as an anode and which one can be used as a cathode, or which one has the higher ability to undergo oxidation and which one has a higher ability to undergo reduction. So based on that, you can actually decide which one is a cathode and which one is an anode. If you happen to see the previous lectures, there we have, I mean, specifically the live interaction session 2 videos, then you will be able to have better this thing. So it totally depends on the electrochemical potential series, the electrochemical potential values. They determine whether how large the value is or how small the value is, determines whether the material will be, or whether the material can undergo reduction or oxidation respectively. So based on that, you can say which material can be used as a cathode, yeah, cathode, and which one can be used as an anode. I hope that clarifies, or else. So anything more to ask, or if you have still anything that is left out to discuss related to this question, then you are welcome to ask. Oh, okay. Okay, in case if you have any questions, then let me know, or otherwise I'll conclude the session for today. So, okay. Thank you for all for joining today's live interaction session. Yes, of course, you can email me if you have. My email ID will be provided along with the presentations. So, this particular lecture, along with the presentation slides, will be made available soon. By the end of this weekend, I mean, either by today or tomorrow, you can access all these live interaction videos as well as the presentation by accessing the course announcement page, where on the left hand side at the bottom corner you can see problem solving session Jan 2026. So if you click on that link, you will be directed to an Excel sheet which contains the link of all these live interaction session videos along with the presentation. If you happen to access the presentation, you will be able to access my email ID. You are always welcome to email me any of your questions. I'll try to answer to them as soon as possible. So I take this as an opportunity to thank Professor Mainak Das sir as well as the NPTEL team for providing me this opportunity to interact with you all in for 4 weeks every Saturday afternoon. So thank you for joining, and I hope all these live interaction sessions were useful to you. So all the best for your NPTEL exam, and thank you, and have a great weekend ahead, and all the best for your future. Thank you, and have a nice weekend ahead.